Hi, everybody. It's Professor Mitchell. We are starting our last chapter today, and that's chapter 9 on conic sections and analytic geometry. So the first section is about the ellipse, which is one of the conic sections. And in this section, we will graph ellipses centered at the origin, write equations of ellipses in standard form, graph ellipses not centered at the origin, and then we'll end with solving an applied problem involving ellipses. So I wanted to start by showing you what we mean when we talk about conic sections. A conic section is formed when a plane intersects with a cone, which in three-dimensional analytic geometry usually means a double cone like the one you see here. So we've already talked about circles. In this section coming up, we're going to talk about ellipses, which are basically ovals. And in the next two sections of chapter 9, we'll talk about parabolas and hyperbolas. All right, so the definition of an ellipse goes like this. An ellipse is the set of all points P in a plane, the sum of whose distances from two fixed points is constant. So those two fixed points are called F1 and F2. And those are called the foci, which is the plural of focus. So I think this GIF, which I found on Google, does a pretty good job of illustrating how you make an ellipse. Imagine taking a piece of string and putting two pins in, let's say, a bulletin board, and then holding the string taut and tracing the curve with your pencil. All right, so notice you've got a red line and a blue line here, and the GIF is showing you that the total length of the blue line plus the red line is remaining constant. So the midpoint of the segment connecting the foci is the center of the ellipse. All right, center means pretty much exactly what you would guess it means. So of course, ellipses have a lot of real life applications. The one that I'm thinking of right off the top of my head is the orbits of planets tend to be elliptical. All right, so an ellipse can be elongated in any direction. The line through the foci intersects the ellipse at 2 points, which are called the vertices, and that's the plural of vertex. The line segment that joins the vertices is the major axis. The midpoint of the major axis is the center of the ellipse. The line segment whose endpoints are on the ellipse that is perpendicular to the major axis is called the minor axis. So the way that I think of this, this is basically what you get if you take a circle and, stretch it in one direction or the other. So what used to be called the diameter of the circle, which of course, if you're talking about a circle, it doesn't matter which direction, it's always going to be the same length. So you can kind of think of it with an ellipse as you have all these different diameters going in different directions. So the longest one is called the major axis and the shortest one is called the minor axis. So if you find that helpful, you can think of it that way. The standard form of the equation of an ellipse should remind you a little bit of the equation of a circle, where the center is at the origin and the major and minor axes have lengths 2a and 2b, is either x squared over a squared plus y squared over b squared equals 1. And in that case, you get a horizontal ellipse. Or x squared over b squared plus y squared over a squared equals 1. Remember, we're assuming that a squared is greater than b squared. So in that case, you would get a vertical ellipse. Notice that if a was equal to b, this would just be a circle. Okay, so I think this is kind of logical. The vertices, again, are on the major axis, a units from the center, and the foci are also on the major axis, c units from the center. For both equations, b squared is equal to a squared minus c squared, or equivalently, c squared is equal to a squared minus b squared. So we'll use those equations in different problems where they give us the foci and ask for the equation of the ellipse, or vice versa. All right, so our first example, we're going to graph this ellipse and also locate the foci. The equation is 16x squared plus 9y squared equals 144. So the first thing I'm going to do is divide this equation through by 144 so that I have the 1 on the right-hand side. So that gives me x squared over 9 plus y squared over 16 equals 1. All right, so the next step is to find the vertices. Because the denominator of y squared is greater than the denominator of x squared, the major axis is vertical. So a squared is equal to 16, which means a equals 4. And that tells us that the vertices are 0, -4, and 0, 4. Now, if you're feeling a little overwhelmed by this, there is, I think, a simpler way to think about this, which is just that the vertices are 2 of the intercepts, all right? Either x-intercepts or y-intercepts. So if you just find your x and y intercepts the way you always do, right? To find y-intercepts, set x equal to 0, and to find x-intercepts, set y equal to 0, you will find your vertices, and you will find your other pair of intercepts. Okay, so that might be an easier way to do it. All right, the endpoints of the minor axis, which in this case would be x-intercepts, are given by b squared equals 9, which means b equals 3. So the endpoints of the minor axis, hold on just one second. Okay, I just noticed a typo there. It was supposed to say the endpoints of the minor axis are -3, 0, and 3, 0, because these are on the x-axis, so it would not have been what it said a moment ago. All right, so now that we know a and b, we can find the foci. Remember the equation c squared equals a squared minus b squared. So that tells us that c squared is equal to 16 minus 9, which is 7. Therefore, c is the square root of 7, which means the foci, which remember are going to be on the vertical axis, are 0, square root of 7, and 0, negative square root of 7. So the graph of this ellipse looks like this. It has 4 intercepts. Y-intercepts at 0, 4, and 0, -4, x-intercepts at 3, 0, and -3, 0, and there are your 2 foci. All right, next example, we're going to find the standard form of the equation of an ellipse with foci at -2, 0, and 2, 0, and vertices at -3, 0, and 3, 0. So this is going to be a horizontal ellipse because the vertices and the foci are on the x-axis. All right, and so the center of the ellipse is midway through between the foci, which would be at 0, 0. That's the only kind of ellipse we've talked about so far. Therefore, the form of the equation is like this: x squared over a squared plus y squared over b squared equals 1. The distance from the center, 0, 0, to either vertex is 3, which means a equals 3. Okay, there's another typo. Let's fix that real quick. Okay, that was a kind of minor typo, but and I wasn't able to edit this line, so I just scribbled that over top. A equals 3, of course, so now we have to find b squared. The distance from the center, 0, 0, to either focus is 2, which means c equals 2. So now we're going to take our equation b squared equals a squared minus c squared and substitute 3 for a. See, they got it right here. And 2 for c, which gives us b squared is equal to 9 minus 4, which is 5. All right, so replacing b squared with 5, you get that the equation is x squared over 9 plus y squared over 5 equals 1. All right, let's get rid of that. Okay, so this is just a summary of how it works when you shift the center away from the origin. It works just like we talked about mostly in chapter 1, I think that was. If you replace x with x minus h, let's assume for a second that h is positive, then that's going to shift the ellipse h units to the right. And if you replace y with y minus k, assuming that k is positive, that's going to shift the ellipse up k units. So no matter what, whether h and k are positive or negative, it's going to shift the center from 0, 0 to hk. So what I find easiest usually with really all of the conic sections is that when they're shifted away from the origin, I start by pretending that they're not. In other words, if there's a minus, h and a minus k there, I start off by ignoring them. And then at the very end, I take my ellipse or my hyperbola or whatever it is, and I shift it so that it has the correct center. Okay. So I don't think of it exactly the way that you see here. Okay, so in this example, we're going to graph the ellipse x plus 1 squared over 9 plus y minus 2 squared over 4 equals 1. All right, so the equation has this form. Note that h is -1 and k is 2, which means the center is -1, 2. Since a squared is greater than b squared, a squared is 9 and b squared is 4. That means the major axis is horizontal and parallel to the x-axis. Okay. So again, the way that I would normally do a problem like this is I would start off pretending like I'm looking at x squared over 9 plus y squared over 4 equals 1. And I would find all the intercepts of that ellipse, the vertices, and also the other two intercepts. And then at the very end, I would take that ellipse and shift it so that it's centered at the point -1, 2. All right. The endpoints of the major axis, which are the vertices, are 3 units to the right and to the left of the center. So that would mean at the points 2, 2 and -4, 2. The endpoints of the minor axis are 2 units up and down from the center. So that would be at the points -1, 4 and -1, 0. So the endpoints of the minor axis are -1, 4 and -1, 0. Which means that your ellipse looks like this. All right, and that brings us to our application problem. A semi-elliptical archway over a one-way road has a height of 10 feet and a width of 40 feet. So the question is, will a truck that is 12 feet wide and has a height of 9 feet clear the opening of the archway? So the reason they're telling you it's a one-way road is because, of course, the truck's best chance of making it under the archway is to drive right in the center of the road, right? Because that's where the arch is the highest. So this is telling you the truck can do that. Okay. All right. So the way that we're going to do this is we're going to construct a coordinate system with the x-axis on the ground and the origin at the center of the archway. So that'll look something like this. Since the arch is 10 feet high at its center, that means that one of the endpoints of the minor axis is at the point 0, 10. And since the archway has a width of 40 feet, that means the vertices are at negative 20, 0, and 20, 0. So this is enough information to find the equation of this ellipse using the equation x squared over a squared plus y squared over b squared equals 1. The equation of the archway is x squared over 20 squared plus y squared over 10 squared equals 1, which means x squared over 400 plus y squared over 100 equals 1. So now to answer the question of whether the truck will be able to clear the archway, the edge of the 12-foot wide truck corresponds to x equals 6. Let's see if you can see that in the picture, right? Because the truck is 12 feet wide. So that means this point right here would be negative 6, 0, and this point right here would be 6, 0. So what we're going to do is we're going to find the height of the archway 6 feet from the center by substituting 6 for x and solving for y. So if you substitute 6 for x, you get 36 over 400 plus y squared over 100 equals 1. So we'll multiply both sides of that equation by 400, and that'll give us 36 plus 4y squared equals 400. Oh, right. And now we'll subtract 36 from both sides, which will give us 4y squared equals 364. Dividing both sides by 4, we get y squared equals 91, which means when x equals 6, y is the square root of 91, which is approximately 9.5. So that means at the side of the truck, the archway is 9.5 feet above the ground, right? Oh, right. And the truck is 9 feet tall. So since the truck is 9 feet tall and at its at the point where the edge of the truck is, the archway is 9.5 feet high, the truck will clear the opening of the archway with about 6 inches to spare. So let me go back to my picture. So what we're saying is, let me turn on my drawing tools here. This point right here is 9 feet above the ground. And this point right here is 9.5 feet above the ground. So the truck will clear the archway. And I believe that's going to take care of section 9.1. So we'll see you next time.